Hello everyone, my name is Walid Al-Hifni and today we are tackling one of the most powerful and elegant concepts in computer science, which is recursion. It's a topic that scares a lot of beginners, but by the end of this tutorial, you'll not only understand it, you'll know exactly how to visualize it. So the content of this tutorial is as follows. We will start with what is recursion and then explain how it is done, followed by two major examples which are the factorial and the Fibonacci, and for each example we will try the iterative loops implementation and then the recursive implementation, and we will also visualize their respective trees. So let's start with what is recursion. Recursion is when a function calls itself to solve a smaller instance of a problem. Imagine a function called dream that calls dream inside itself. In theory, this would go on forever. So if we do not tell it when to stop, your program crashes. So we can think of recursion like the Russian nesting dolls. You open one doll to find a smaller one inside. You keep doing this until you reach the smallest doll that cannot be opened. This structure gives us the two golden rules of recursion. So every recursive function needs two parts. First, the base case. This is the stop sign. Without it, you get an infinite loop. And in our previous example, it represented the smallest doll. We stop when we reach the smallest doll. Second, the recursive step. This is where we break the problem down into a smaller piece. And in our previous example, this represented opening a doll. So basically, the base case is the condition that stops the recursion, while the recursive step is when the function calls itself with a smaller input. So a question is, how does the computer remember where it was? It uses the call stack. Imagine a stack of plates. Every time a function calls itself, the computer adds a plate to the stack. When it hits the base case, it starts removing them one by one from top to bottom, passing the answers back down. So basically, push means adding a new function call on the top, while pop means removing a finished function call from the top. So the main question is, when to use iteration or loops and when to use recursion. For iteration or loops, the visual shape is a linear straight line. It goes one step at a time straight down. Meanwhile, for recursion, it is a branching tree. It splits and branches out like roots growing. Therefore, iteration or loops are best used for simple lists, counting and summing, while recursion is best used for sorting, mazes, AI, and file systems. And now, moving on to the pros and cons of each approach, iteration or loops are faster and have efficient memory usage. However, the code can get messy for complex logic. On the other hand, recursion has a cleaner code and handles complexity better. However, it can crash if too deep, resulting in a stack overflow. So now, let's verify this by writing some actual code. Let's start with a classical example, which is the factorial problem. In simple words, a factorial is just a mathematical way of telling you to multiply a number by every number smaller than it down to 1, and it is written using an exclamation mark. So if I write 3 followed by an exclamation mark, it refers to 3 factorial, which is 3 multiplied by 2 multiplied by 1, and in this case the result is 6. Another example is 5 factorial, which is 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1, and the result is 120. However, there are two quick rules. The first rule, 1 factorial is just 1, and the second rule, 0 factorial is also 1, and this is a special mathematical rule to make the formulas work. And now, if we want to implement the factorial functionality using loops, we can define a function called factorial underscore iterative, which takes our number as an input argument, and then inside of the body of this function, we initialize the result variable by 1, because the factorial of the smallest number we have, which is 0, is actually 1. So 0 factorial is 1, and also 1 factorial is 1. So we initialize the result variable by 1. And then we implement our while loop, which is while n is greater than 1. We perform the following operation, which is result equal result multiplied by n. And then we need to decrement the n variable by 1. So n equal n minus 1. Afterwards, we return the result. So if we try it and we say print factorial underscore iterative of 3, it should actually output 6. And now let's trace our code when n is equal to 3. First of all, we initialize the result variable by 1, and the result variable will be the variable that we will return at the end of the function. And then in the next step, we check on the while loop condition. Is n greater than 1 or not? And here n is equal to 3. So is 3 greater than 1? Yes, this condition is actually true. Therefore, we will execute the body of the while loop and we move on to this statement. Result equal result times n. So basically, result is equal to the old value of the result variable, which is 1, multiplied by n, which is 3. So 1 multiplied by 3 is 3. And then we decrement the n variable by 1. So n is equal to n, which is 3 minus 1, and the result is 2. So now the n variable contains the value 2. Now we move back to the while loop condition and we check, is the new n variable, which is 2, greater than 1 or not? Yes, this condition is true. Therefore, we will execute the body of the while loop for a second time. Here we will update the result variable. Currently it holds 3. So 3 multiplied by n, which is 2, is equal to 6. And this is the new value that will be stored inside of the result variable. And then we move on to decrementing the n variable by 1. Currently the n variable contains the value 2. So 2 minus 1 is equal to 1. And then we move back to the while loop condition and we check, is the new n variable, which is 1, greater than 1 or not? This condition is false because 1 is not greater than 1. 1 is equal to 1. So here we skip the body of the while loop and we move on to the next statement outside of the while loop, which is the return statement. And here we will return the result variable, which contains the value 6. So if we try it with another number, for example 5, it should output 120, as you can see. However, if you are not a fan of while loops and you prefer for loops, we can actually implement the factorial functionality using for loops. So we will comment this while loop and we will replace it with a for loop by writing for I in range from 1 inclusive till n plus 1 exclusive. Because if you recall, the start value of the range is inclusive, which means it is included in the range. However, the stop value of the range is exclusive, therefore it is not included in the range. So if it is not included in the range, I will not be able to multiply it by the previous numbers. So for example, if n is equal to 3, I want to calculate the factorial of 3. It is 3 times 2 times 1. So I need my range function to create a range containing the values 3, 2, and 1. Therefore, 3 should be included. However, if I only have here n and not n plus 1, then 3 will not be included because this stop value is exclusive and not inclusive. So we say n plus 1, which is 3 plus 1, which is 4, which means the range function will create a range containing the values 1, 2, and 3, and it will stop at 4 and it will not include 4 in my range. Then the next step inside of the for loop body, we will actually write result equal result multiplied by I, and that's it. So if we try to call the function with n equals 3, it should output 6, as you can see. Now, if we trace our code with n equals 3 At the beginning, we initialize the result variable with 1 as we did in the previous example. And then we move on to the for loop, but first we evaluate the range function, which will return a range of numbers. This time the range will contain only 3 values, 1, 2, and 3, because the start value, which is inclusive, is 1, and the stop value, which is exclusive, is 3 plus 1, which is 4. So it will actually return a range of values from 1 till 3 inclusive, which are 1, 2, and 3. And since the returned range contained 3 values, so this loop will iterate 3 times. We will start first by I equal 1, which is the first value inside of our range, and then we move on to the body of the for loop and we execute result equal result times I. The initial result value is actually 1, so 1 multiplied by I, which is 1, and the new value of the result variable will also be 1. And then we move back to the for loop, and since there are still values in the range, we move on to the second value in the range, so I is equal to 2 this time, and then we move on to the body of the for loop. The current result value is actually 1 multiplied by the current I value, which is 2, so 1 multiplied by 2 is actually 2, and then we move back to the for loop and we update the I value to contain the third and last item in our range, which is 3, and then we move on to the body of the for loop. This time the result variable contains 2 multiplied by the I variable, which is 3, so 2 multiplied by 3 is actually 6, and then if we move back to the for loop, there are no longer any items or values in our range. So we exit the for loop and we return, or we move on to the return statement, which will return the result, which is 6. So if we try it with another number, for example 5, it should output 120. And now let's try to implement the factorial function using recursion. But first, we need to visualize how the factorial is actually being calculated. For example, if we say 5 factorial, it's basically equal to 5 multiplied by 4 multiplied by 3 multiplied by 2 and finally multiplied by 1. We can also say that 5 factorial is equal to 5 multiplied by, and if you see the subset, we can call it 4 factorial, because 4 factorial is 4 times 3 times 2 times 1. So 5 factorial is basically you multiply 5 by 4 factorial. And then we can say that 4 factorial is basically 4 multiplied by 3 factorial. So we can write here 4 multiplied by 3 factorial, because 3 factorial is 3 times 2 times 1. So basically 4 times 3 times 2 times 1 is 4 factorial. And we can continue with this sequence. We can say that 3 factorial is just 3 multiplied by 2 factorial. So we can write here 3 multiplied by 2 factorial. Since 2 factorial is 2 times 1, so 3 times 2 times 1 is actually 3 factorial. And we can continue with the rest of the sequence. We can say that 2 factorial, it is just 2 multiplied by 1 factorial. So we can write 2 multiplied by 1 factorial. And let's not forget that 1 factorial is actually 1. So that's our base case, like 0 factorial, which is also 1. So if we would like to visualize it as a tree, we can say that 5 factorial is just 5 multiplied by 4 factorial. And 4 factorial is just 4 multiplied by 3 factorial. And 3 factorial is just 3 multiplied by 2 factorial. And 2 factorial is just 2 multiplied by 1 factorial. And finally, 1 factorial is just 1. So as you can see, we reached our base case, which is 1 factorial equal 1. Now we need to move upwards and substitute. So basically, we will replace 1 factorial by 1, which is its value. Then 2 times 1 is 2. So we replace 2 factorial by 2. And then 3 times 2 is 6. So we replace 3 factorial by 6. And then 4 times 6 is 24. So we replace 4 factorial by 24. And finally, 5 times 24 is 120. So 5 factorial is equal to 120. And that's our final answer. So in terms of programming and recursion, we can think about it like this. If we have our function factorial of 5, it will return the following: 5 multiplied by factorial of 4. And then factorial of 4 will return the following: 4 multiplied by factorial of 3. And then factorial of 3 will return the following: 3 multiplied by factorial of 2. And then factorial of 2 will return the following: 2 multiplied by factorial of 1. Now, factorial of 1 will return 1 because it is the base case. So here, factorial of 1 will evaluate to 1. Factorial of 2 will evaluate to 2 times 1, which is 2. And here, factorial of 3 will evaluate to 3 times 2, which is 6. And then factorial of 4 will evaluate to 4 times 6, which is 24. And finally, factorial of 5 will evaluate to 5 times 24, which is 120. So now, if we go back to our editor and write our recursion function, it will be as follows. We will create a new function and we call it Factorial underscore recursion, and it also takes n. The first thing we need to do is create our base case, which is if n is less than or equal to 1, so we can handle the two base cases, 0 factorial and 1 factorial. Both of them result in 1, so here we will return 1, else we will do the following, which is return n multiplied by factorial underscore recursion of n minus 1. And here our function ends. Now let's test our function. Here we are going to replace this print statement and call our new function factorial underscore recursion, and let's try it on a small number like 3. 3 factorial is 6, so as you can see it printed out 6. If we try it with 5, it should output 120. As you can see, it printed out 120. Now, if we try to trace this function using a small n, for example, n equals 3, the first thing it will do is to check on the base case if n is less than or equal to 1. So here, is 3 less than or equal to 1? The answer is no. So this condition will evaluate to false and it will move to the else part. Here in the else part, it will return the following. It will return n, which is 3, multiplied by factorial underscore recursion of n minus 1. 3 minus 1 is 2. So it will call itself, but this time with an n equal to 2. So we call the function again, but this time n is equal to 2, and we will check on the base case. Is 2 less than or equal to 1? No, this condition is false. So we will move to the else part. Here in the else part, it will return n times factorial underscore recursion of n minus 1. So we will replace the factorial underscore recursion of 2 with the expected return item based on this call, which is actually 2 multiplied by factorial underscore recursion of n minus 1, and 2 minus 1 is actually 1. And we put it inside of brackets just to indicate that this whole term refers to the returned value from factorial underscore recursion of 2. Then, as you can see inside of it, there is another call. So this function calls itself again, but this time with a different n, which is 1. So here n is equal to 1, and we will check again on the base case. Is 1 less than or equal to 1? Yes, this condition is true because 1 is equal to 1. So we will execute the body of the if statement and we will return 1. So here, factorial underscore recursion of 1, it will return the value 1. So now we can do the substitution that we've seen in the previous visualization when we started from bottom to top, because now we reached the base case. So there are no longer any recursive calls, which means that this function is no longer calling itself again. So we can actually evaluate the terms because we have all of the numbers available. Here, if we start from bottom to top, we have 2 times 1, which evaluates to 2, and then 3 times 2, which evaluates to 6. So the final return value of this function is 6. Now let's move on to a harder example, which is the Fibonacci sequence. The Fibonacci sequence is a sequence in which each element is the sum of the two elements that precede it. In other words, each number is the sum of the two previous numbers. First, we have two base cases. The first one is Fibonacci of 0, which is equal to 0, and the second one is Fibonacci of 1, which is equal to 1. And then our sequence continues normally. So for example, Fibonacci of 2 is actually equal to Fibonacci of 1 plus Fibonacci of 0, which is 1 plus 0 equal to 1. So Fibonacci of 2 is equal to 1. And then if we want to continue, Fibonacci of 3 is equal to Fibonacci of 2 plus Fibonacci of 1, which is equal to 1 plus 1, and the result is 2. And then one last example, Fibonacci of 4 is equal to Fibonacci of 3 plus Fibonacci of 2, which is equal to 2 plus 1, and the result is 3. So we can say that Fibonacci of n is equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2, which is only valid for n greater than 1, because Fibonacci of 0 is equal to 0 and Fibonacci of 1 is equal to 1. So we can define the Fibonacci sequence by this recurrence relation. Now let's implement our Fibonacci sequence using loops, and this time I will be using a simple while loop implementation rather than the complex for loop implementation. So let's define our function Fibonacci underscore iterative, which takes n as an input argument. And then we define our base cases. If n is less than or equal to 1, we just return n. Because if n is equal to 0, this condition will be true because 0 is less than or equal to 1. So it will return 0. And if you remember, Fibonacci of 0 is actually 0. And also, if n is equal to 1, then this condition will also be true because 1 is less than or equal to 1. So it will return 1. And if you recall, Fibonacci of 1 is equal to 1. And then if n is not equal to 0 or equal to 1, we continue with our code. However, we first need to define two variables. A is equal to 0, which is the result of Fibonacci of 0, and b is equal to 1, which is the result of Fibonacci of 1. And then we define a variable called step equal to, which is the first number or n that is not handled by our base case. Since 0 and 1 both are handled by our base case, so 2 is the first number that is not handled by our base case. And then we move on to our while loop, and here, while our step is less than or equal to n, we perform the following operations. First, we perform the addition of the Fibonacci of step minus 2 and the Fibonacci of step minus 1. So here we create a temporary variable called temp is equal to b plus a, where b is actually the Fibonacci of step minus 1, and A is equal to the Fibonacci of step minus 2. Because initially step is equal to 2. So 2 minus 1 is 1. So actually B is Fibonacci of 1, which is here Fibonacci of 1. And here 2 minus 2 is 0. So here A is equal to Fibonacci of 0. And as you can see, A contains the value of Fibonacci of 0. So here we are performing the very first time the Fibonacci of 1 plus the Fibonacci of 0. And then we need to loop until we reach our n. Because, for example, if n is equal to 3, here in the first iteration, we only perform the Fibonacci of step, which is 2. However, we need to increment our step until we reach n. So here, step is equal step plus 1. We will continue executing this while loop until we reach our n. And then we need to update our A and B variables to contain the new Fibonacci values based on the new step value. So for example, in the first iteration, here the new step size will be step, which is 2 plus 1, which is equal to 3. So A needs to have the result of Fibonacci of step minus 2, which is equal to Fibonacci of 3 minus 2, which is equal to the Fibonacci of 1. And the Fibonacci of 1 is actually stored in the B variable. So we can just say A is equal to B. And then B needs to have the result of Fibonacci of step minus 1, which is equal to the Fibonacci of 3 minus 1, which is equal to the Fibonacci of 2. And here, if you recall, the temporary variable contains the result of the Fibonacci of 2 because it has the addition of Fibonacci of 1 plus Fibonacci of 0. So we can simply say B is equal to temp, and then outside of the while loop, we can return B. So if we want to test our function, let's print the Fibonacci underscore iterative of 2. It should output 1. As you can see, it printed out 1. Let's try it with 3. Fibonacci of 3, it should be 2. So if we click on the run button, as you can see, it printed out 2. Also, let's try it with Fibonacci of 4. It should output 3. As you can see, it printed out 3. And if we try it with one of our base cases, for example, Fibonacci of 0, it should output 0. As you can see, it printed out 0. And Fibonacci of 1, it should print out 1, as you can see. And now let's trace our code step by step, and let's, for example, trace it with Fibonacci of 4, which is equal to 3. Here n is equal to 4, and then we move on to the body of the function. And here we see the condition if n is less than or equal to 1. Is 4 less than or equal to 1? No, this condition is false. Therefore, we will skip the if condition and move on to the initialization of our variables. Here we initialize the variable A with the result of Fibonacci of 0, which is 0, and then we initialize the variable B with the result of Fibonacci of 1, which is 1. And then we initialize our step variable with 2, which is the first number that is not handled in our base case. And then we move on to our while loop condition. Here we are checking whether step is less than or equal to n. So, is the step value, which is 2, less than or equal to n, which is 4? Yes, this condition is true. Therefore, we will execute the body of the while loop. And let's just remove all of these examples we had in the previous scenario. And let's actually start with the first statement in our while loop. And here we have temp equal B plus A. And we can think about temp as if it is the Fibonacci of the step. So we can say that temp is equal to the Fibonacci of the step, where B is equal to Fibonacci of step minus 1 and A is equal to Fibonacci of step minus 2. So basically, temp is equal to the Fibonacci of the step, which is 2, which is equal to B plus A. And here we have B is equal to 1 and A is equal to 0. So temp will contain the value 1. Because the Fibonacci of step minus 1, which is 2 minus 1, which is 1, is actually B, which is here, while the Fibonacci of step minus 2, which is 2 minus 2, which is 0, so the Fibonacci of 0 is actually A. Therefore here temp is equal B plus A, which is 1 plus 0, and the result is 1. Then we move on to the next step, which is incrementing the step size by 1. So actually the step value is 2 plus 1 is equal to 3. So the new step value is 3. And since we updated our step value, we need to also update our A and B variables, because A represents the result of Fibonacci of step minus 2 and B represents the result of Fibonacci of step minus 1. So here, if I want A to contain the value of Fibonacci of step minus 2, which is actually the Fibonacci of the current step, which is now 3 minus 2, which is equal to the Fibonacci of 1. So which variable contains the result of the Fibonacci of 1? As you've seen before, it is B. Therefore here I say A equal B. And thus A will contain the value 1. And then here I want B to contain the value of Fibonacci of step minus 1, which is the Fibonacci of 3 minus 1, which is equal to the Fibonacci of 2. Now, which variable here contains the result of the Fibonacci of 2? As you've seen before, temp contains the result of Fibonacci of 2. Therefore, I say B equal temp to contain the result of Fibonacci of 2, which is also 1. Now, we move back to the while loop condition. Our new step value is actually 3. So is 3 less than or equal to 4? Yes, this condition is true. Therefore, we will execute the body of the while loop. But this time, we are going to calculate temp equal B plus A. And this will be the Fibonacci of the new step, which is Fibonacci of 3. Fibonacci of 3 is actually Fibonacci of 2 plus Fibonacci of 1. So here, B contains the Fibonacci of 2, A contains the Fibonacci of 1. Therefore, here B plus A is equal to 1 plus 1, which is equal to 2. So now the temp variable contains the value 2. And then we need to increment our step by 1. So the current step value is 3. 3 plus 1 is equal to 4. So the new step value is equal to 4, which means we need to update our A and B variables. A should contain the Fibonacci of step minus 2, which is now 4 minus 2, which is the Fibonacci of 2. And the Fibonacci of 2 is actually 1. And then here B needs to contain the result of the Fibonacci of step minus 1, which in this case will be 4 minus 1, which will be 3, and the Fibonacci of 3 is actually 2, as we've seen here when we calculated it. And then we move back to our while loop condition and we check, is the current step value 4 less than or equal to 4? Yes, this condition is true because 4 is equal to 4. So we move on to the body of the while loop, and now we try to calculate the Fibonacci of the step. This time it will be the Fibonacci of 4. So the Fibonacci of 4 is equal to B plus A. B is actually 2 and A is still 1. So 2 plus 1 is 3. And then we increment our step by 1. So 4 plus 1 is actually equals to 5. And since we updated our step variable, we also need to update our A and B variables. So A is equal to B, which is Fibonacci of step minus 2, which is now Fibonacci of 5 minus 2, which is Fibonacci of 3, and here it is equal to 2. And then when we update our B variable, B equal temp, which is Fibonacci of step minus 1, which is Fibonacci of 5 minus 1, which is Fibonacci of 4, and as you've seen here, Fibonacci of 4 is actually equal to 3. And then we move back to our while loop condition and we check, is the new step value, which is 5, less than or equal to 4? No, this condition is false. Therefore, we will not execute the body of the while loop and we will move on to the next statement, which is returning B. But why did we return B? Because if we recall, the last operation we performed inside of the while loop is assigning the result of the Fibonacci of 4 to B. And 4 is actually the n that we started the function with. So actually we started with n equal 4. Therefore here, B is equal to Fibonacci of 4, which is actually Fibonacci of n, the result that we want to actually return from this function, which is actually 3. So this function will return b, which contains 3, which is Fibonacci of 4, which is the Fibonacci of n, the n that was given as an input argument to our function here. And now let's implement the Fibonacci sequence using recursion. But first we need to visualize how does the Fibonacci sequence work. So first let's recall our base cases. We had Fibonacci of 0 equal to 0 and Fibonacci of 1 is equal to 1. And then we have our general rule, which is Fibonacci of n is equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2. So now if we try it with a simple example like Fibonacci of 4, where here n is equal to 4, we can apply the general rule, which is as follows. So Fibonacci of 4 is Fibonacci of 4 minus 1, which is Fibonacci of 3, plus Fibonacci of 4 minus 2, which is Fibonacci of 2. So Fibonacci of 4 is Fibonacci of 3 plus Fibonacci of 2. However, Fibonacci of 3 and Fibonacci of 2 are not our base cases, so we need to continue this tree. So here Fibonacci of 3 is basically Fibonacci of 3 minus 1, which is Fibonacci of 2, added to Fibonacci of 3 minus 2, which is Fibonacci of 1. And also Fibonacci of 2 on the right hand side is basically Fibonacci of 2 minus 1, which is Fibonacci of 1, added to Fibonacci of 2 minus 2, which is Fibonacci of 0. So basically Fibonacci of 3 is Fibonacci of 2 plus Fibonacci of 1, and here Fibonacci of 2 is Fibonacci of 1 plus Fibonacci of 0. And as you can see, Fibonacci of 1 and Fibonacci of 0 are our base cases. However, Fibonacci of 2 is not a base case, so we need to continue with our tree. So here, Fibonacci of 2 is Fibonacci of 2 minus 1, which is Fibonacci of 1, plus Fibonacci of 2 minus 2, which is Fibonacci of 0. And we do not forget the plus sign. Now we need to evaluate all of our base cases. So here Fibonacci of 1 is actually 1, Fibonacci of 0 is actually 0, Fibonacci of 1 is also 1, Fibonacci of 1 is 1, and finally Fibonacci of 0 is 0. And now we need to evaluate our tree from bottom to top. But first we start from the leftmost item, which is this one, the result of the base case Fibonacci of 1. So here we are going to replace Fibonacci of 1 with its result, which is 1, and also here we have 0, which is the result of the base case Fibonacci of 0. So we are going to replace Fibonacci of 0 with its value, which is 0. And then we perform the addition, so 1 plus 0 is 1, and we are going to replace Fibonacci of 2 with 1. And then we move on to the right hand side and we see Fibonacci of 1. Here Fibonacci of 1 evaluates to 1 because it is a base case. So we are going to replace Fibonacci of 1 with 1, and then we perform the addition. 1 plus 1 is 2, so we are going to replace Fibonacci of 3 with 2. And then we move on to the right hand side and we go to the leftmost item, which is this one, and it is the result of Fibonacci of 1 because it is a base case. So we are going to replace Fibonacci of 1 with 1, and then on the right hand side we also see 0, which is the result of Fibonacci of 0, which is also a base case. So we are going to replace Fibonacci of 0 with 0. And here we perform the addition, so 1 plus 0 is 1, so we are going to replace Fibonacci of 2 with 1. and then we perform the addition. So 2 plus 1 is 3, and we are going to replace Fibonacci of 4 with 3, which is our final result. Fibonacci of 4 is actually equal to 3. So now let's move back to our editor and implement our recursive function. First, let's define our recursive function. Let's call it Fibonacci underscore recursion, which takes n as an input argument. And then we implement our base case, which is similar to the iterative version. If n is less than or equal to 1, we just return n. Because when n is equal to 0, it should return 0, and when n is equal to 1, it should return 1. So basically it is just returning n. And then we should actually implement our recursive step, which is exactly like the general formula we had. We say here return Fibonacci underscore recursion of n minus 1 plus Fibonacci underscore recursion of n minus 2. And if we want to test our new function, we can actually test it with Fibonacci of 4, because we know the answer is actually equal to 3. Therefore here we can say Fibonacci underscore recursion of 4, and we click on the run button. As you can see, it printed out 3. If we try it with Fibonacci of 3, it should output 2, as you can see. Now let's trace our function with an example like n equal to 4, and it will be very similar to the tree that we actually traced before. Now we enter the body of the function and we see the if condition. If n is less than or equal to 1, is 4 less than or equal to 1? No, this condition is false. Therefore I will skip the if condition and move on to this return statement. However, this part is very tricky, because here we have two recursive calls, Fibonacci of n minus 1 and Fibonacci of n minus 2. However, the computer cannot do two parallel calls at the same time. Therefore, it starts with the leftmost call, which is Fibonacci of n minus 1. So we can visualize it as follows. We can say that we have Fibonacci of n minus 1, which is 4 minus 1, plus Fibonacci of n minus 2, which is 4 minus 2, which is equal to Fibonacci of 3 plus Fibonacci of 2. However, as I told you before, we will evaluate Fibonacci of 3 first and everything under Fibonacci of 3, and then when we finish the whole branch of Fibonacci of 3, we will return to evaluate Fibonacci of 2. And we can say that this term is the result of Fibonacci of 4 when n is equal to 4. Now, as I said before, we will evaluate the leftmost term first, which is Fibonacci of 3. Now our n is equal to 3, and here we will check on the condition. Is 3 less than or equal to 1? No, this is false. Therefore, we will skip the if condition and move directly to the return statement. And this time, we are evaluating Fibonacci of 3. So it will be Fibonacci of n minus 1, which is 3 minus 1, plus Fibonacci of n minus 2, which is 3 minus 2, which is equal to Fibonacci of 2 plus Fibonacci of 1. So what does the computer see? This Fibonacci of 3 is replaced by Fibonacci of 2 plus Fibonacci of 1. So we can do something like this. We can remove it, and we can actually add instead of it Fibonacci of 2 plus Fibonacci of 1. Because Fibonacci of 3 as a term evaluated to Fibonacci of 2 plus Fibonacci of 1. And then we will continue with the leftmost call, which is Fibonacci of 2, which is this Fibonacci of 2, because they are the same. So here n is equal to 2, and we will check the if condition. Is 2 less than or equal to 1? No, this condition is false. Therefore, we will move directly to the return statement. So it means that Fibonacci of 2 is equal to Fibonacci of n minus 1, which is 2 minus 1, plus Fibonacci of n minus 2, which is 2 minus 2, which is equal to Fibonacci of 1 plus Fibonacci of 0. And if you remember, this Fibonacci of 2 is exactly this Fibonacci of 2. And we evaluated this Fibonacci of 2 to Fibonacci of 1 plus Fibonacci of 0. So we can replace both Fibonaccis of 2 with this new term. So here we can replace it and we can say Fibonacci of 2 is actually Fibonacci of 1 plus Fibonacci of 0. And we can also replace this Fibonacci of 2 with Fibonacci of 1 plus Fibonacci of 0. Now we will continue with the leftmost term, which is Fibonacci of 1. So n is equal to 1. And then we will check on the if condition. Is 1 less than or equal to 1? Yes, this condition is true because 1 is equal to 1. So we are going to return n, which is 1. So we can add the Fibonacci of 1 result to our comments list. We can say that Fibonacci of 1 evaluated to 1. And if you remember, this Fibonacci of 1 is exactly the same as this Fibonacci of 1 and this Fibonacci of 1. So we can replace this Fibonacci of 1 with its result, which is 1. And we can also replace this Fibonacci of 1 with 1 and this Fibonacci of 1 with 1. Now we need to continue with our code, and here the remaining call that was not evaluated is Fibonacci of 0. So by default we are going to call Fibonacci of 0. So here n is equal to 0, and we are going to check on the if condition. Is 0 less than or equal to 1? Yes, this condition is true. Therefore we are going to return n, which is 0. So we can add it to our list and we can say Fibonacci of 0 is equal to 0. And then here, if we go upwards, we can replace Fibonacci of 0 with its result, which is 0. And if we go one step upwards, we can also replace this Fibonacci of 0 with 0. And finally, if we go one step upwards, we can replace this Fibonacci of 0 with 0. And now we can evaluate the term 1 plus 0 is equal to 1. And here we can replace this term by 1 because 1 plus 0 is 1. And here 1 plus 0 is 1. And as you can see, Fibonacci of 2 evaluated to 1. So every time we saw Fibonacci of 2 in this branch of the tree, we replaced it with 1. Like here, originally we had Fibonacci of 2, but we replaced it with 1. And here we also had Fibonacci of 2, but we replaced it with 1. Now let's continue, and the leftmost term that was not evaluated is this Fibonacci of 1. So here we have n is equal to 1. And then we check on the if condition. Is 1 less than or equal to 1? Yes, this condition is true. Therefore, we are going to return n, which is 1. And now let's add it to our list. Here we will say Fibonacci of 1 is equal to 1. And take care, this Fibonacci of 1 is different from this Fibonacci of 1. These are two different calls. Therefore, it is executed twice. Now Fibonacci of 1 is equal to 1, so we are going to replace this Fibonacci of 1 with its result, which is 1. And if we move upwards, we are going to replace this Fibonacci of 1 with 1. And here 1 plus 1 is equal to 2, and also 1 plus 1 is equal to 2. So as you can see, Fibonacci of 3 evaluated to 2. So every time we've seen Fibonacci of 3 in this branch of the tree, we replaced it with 2 like this one. And finally, the only remaining term is Fibonacci of 2. So here we are going to call the function with n equal to 2. And here we are going to check on the if condition. Is 2 less than or equal to 1? No, this condition is false. Therefore, we are not going to execute the body of the if statement, and we are going to move to the return statement. So let's write it here. Fibonacci of 2 is equal to Fibonacci of n minus 1, which is Fibonacci of 2 minus 1, plus Fibonacci of n minus 2, which is Fibonacci of 2 minus 2, which is equal to Fibonacci of 1 plus Fibonacci of 0. And then we can replace Fibonacci of 2 with this term. So here Fibonacci of 2 will be replaced with this term, which is Fibonacci of 1 plus Fibonacci of 0. Now, the rule is we will execute or call the leftmost term, which is here Fibonacci of 1. So n is equal to 1, and we are going to check on the if condition. Is 1 less than or equal to 1? Yes, this condition is actually true. So we are going to enter the body of the if condition and return n, which in this case is 1. So we can add this result to our list. Fibonacci of 1 is equal to 1, and then we can replace this term Fibonacci of 1 with its result, which is 1. And if we go upward in the tree, we can replace this term 2, which is Fibonacci of 1, with 1. Now the only remaining term is Fibonacci of 0, so we are going to call the function with n equal to 0, and here we will check on the if condition. Is 0 less than or equal to 1? Yes, this condition is true, therefore we are going to return n, which is 0. So if we add it to our list, we can say that Fibonacci of 0 is equal to 0. And then we can replace this Fibonacci of 0 with its result, which is 0. And if we move upwards in the tree, we can replace this Fibonacci of 0 with 0. And if we perform the addition, Fibonacci of 2 is equal to 1 plus 0, which is 1. And we can also evaluate this term 1 plus 0 is equal to 1. So here, every time we've seen Fibonacci of 2 in this branch of the tree, we replaced it with 1, like here and here. Now, finally, we can evaluate the result of Fibonacci of 4, which is 2 plus 1, which is 3. Which means that this function will return 3 because we reached the top of the tree, which is Fibonacci of 4. So Fibonacci of 4 is equal to 3, and this will be the returned value from the function. So if we call Fibonacci underscore recursion on 4, it should return 3 as we traced it. Now we are done with the recursion tutorial. Thanks for watching. I hope you enjoyed it and learned how to implement recursive functions in Python. If you have any questions, don't hesitate to write them in the comments. Also, you can check out my Introduction to Python Programming for Beginners crash course on my channel, which covers many other Python concepts. Moreover, if you liked the video, don't forget to like, comment, share and subscribe to the channel. Finally, you can write in the comments what programming topics you want to learn next. See you in the next video and goodbye.